Hello friends, today we are going to discuss about a very interesting problem. This problem comes from the topic of conservation of energy. Problem is very simple, very classic problem. Imagine there is a hemispherical dome on which a mass m is resting on the top. When we are giving a gentle push to the mass m, so the mass m travels along the surface of the hemispherical dome, and at a particular point it loses the contact from the dome and slowly it falls on the ground. Here, one thing we need to assume that the surface of this hemispherical dome is frictionless. It does not have any friction. Very important assumption. There is also a problem where friction is considered, but right now for this problem, we are not going to consider the friction. Now, the question being asked here is, what is the angle theta at which the mass m is going to lose the contact from the sphere, and after losing the contact from the sphere, what it is going to do? Okay. Now, to solve this problem, we need to apply two laws. One is the conservation law of energy. Okay. Let's do it like this. Mass m has traveled from the position 1 to position 2. Of course, in traveling from position 1 to 2, it has swept the angle theta. Now, how much height did the mass m descend is very important for us, because that is nothing but loss of potential energy of the mass m. Let us take the radius of the sphere as r. Now, the height, the vertical height difference from the position 1 to position 2 is r minus r cos theta. Yes, because if we consider this as O, this as A, this as B, the length of OA is r cos theta, because the radius of the sphere is going to be same, r cos theta. So the distance from the position A and B, AB, the vertical distance is going to be r minus r cos theta. Now if I say mg into r into 1 minus cos theta, it is loss of potential energy. The loss of potential energy which happened from the point 1 to point 2 should transform into kinetic energy. Since it is frictionless, we are assuming that the work done against the friction need not be taken into account. So we can do one thing. We can equate it to the change in potential energy, which is equal to half m v square. Now, half mv square is the absolute velocity of the mass m. Very important point to be taken into consideration. It is not a horizontal velocity, nor it is the vertical component of the velocity, but it's the absolute velocity, and its direction is tangential to the surface of the sphere. I'm showing with this arrow indication because as long as it is in touch with the sphere, it is constrained to move along the surface of the sphere, and it is supposed to perform a circular motion. So v is nothing but the tangential velocity of the mass m with respect to the circle. Mg r into 1 minus cos theta is equal to half mv square, which we can take it as equation 1. Equation 2. Let's draw the free body diagram. Let's draw the free body diagram of mass m. Here, if we observe, it is making theta with vertical axis. The gravitational component mg is acting in the downward direction. Normal reaction force is acting on the surface on which mass m is resting, so which we can take in this particular direction, and we can call it as equal to n. And apart from that, there is one more important force which is acting, that is nothing but the radial component of the acceleration, which is acting outwards, which is equal to mv square by r. Now mv square by r, n, they are acting outwards. Mg cos theta, that is the component of the weight of the object along the radius, is going to be equal to mg cos theta. So applying the Newton's third law, mg cos theta is equal to n plus mv square by r. When a body is moving on the surface, a situation comes where it loses contact from the surface. At that time, we say that the normal reaction force is zero. Means the condition for this object to lose the contact from this hemispherical dome is mg cos theta is equal to mv square by r, because n is equal to 0. Now we can cancel m and m. So v square is equal to r into g into cos theta. This is the conclusion what we can draw from this. Now time has come where we have to use the equation 1. Of course, we are going to cancel m and m. So v square on the other hand can be written as v square is equal to g into r into 1 minus cos theta. V square is equal to g into r into 1 minus cos theta. We are going to substitute that value, g into r into 1 minus cos theta. Two g into r, sorry friends, 2g into r into 1 minus cos theta. 2g into r into 1 minus cos theta becomes equal to g into r into cos theta. Again I am repeating, when I say normal reaction force n is equal to 0, g cos theta becomes equal to v square by r. V square can be written as g into r into cos theta. Going back to the first equation, which involved the conservation of energy principle, we say that v square is equal to 2 into g into r into 1 minus cos theta. So we are going to substitute the value of the v square which we obtained in the equation 1 in equation 2. V square is nothing but 2gr into 1 minus cos theta, and we are going to substitute here. Now g and r will cancel. Okay. G and r will cancel. So we finally end up calculating cos theta is equal to 2 by 3. Theta is equal to cos inverse of 2 by 3. So this is the point at which it is going to lose the contact. After losing the contact, what does it happen for the mass m? So taking v as the initial velocity, it is as if we have projected an object from some particular height, such that it is making 90 minus theta with the horizontal, and its initial velocity is equal to v. It becomes a pure projectile motion. In many situations, they ask the question, how far from the center of the sphere will the mass m fall on the ground?